play with each other. We did the standard model as an effective field theory, higher dimension operators in the standard model. And then we started talking about taking the standard model as theory one and removing things from it. In particular, constructing what's called the weak Hamiltonian by removing the top W, Z, and Higgs from the standard model. And last time we were focusing on the anomalous dimensions and things about renormalization. So we had this equation for the weak Hamiltonian for a particular case of B goes to C, U bar D. That was the case that we just decided to study rather than the full Hamiltonian. So there was some prefactor. We had two operators with Wilson coefficients and operators. These are four fermion operators. And there was different bases. We could write them in the bare form, or we could write them in renormalized coefficient and renormalized operator. And then we could do it either in the 1-2 basis or the plus-minus basis. So the plus-minus basis is just linear combinations of the 1-2. The advantage of if you're in the 1-2 basis, then you have this mixing matrix. So it's a 2x2 matrix. If you're in the plus-minus basis, then at least at lowest order, it's a simple product equation. So plus doesn't interfere with minus. Okay, so that's where we got to, and we'll just continue today. So we had these anomalous dimension equations for the operators. We can also write down anomalous dimension equations for the Wilson coefficients. How do we do that? Well, the way that we do that is we make use of the fact that if we look at the first line here, there's no mu. So the Hamiltonian is mu independent. That means that the mu dependence of the coefficient cancels the mu dependence of the operator. And we can use that to take an anomalous dimension equation for the operator and turn it into one for the coefficient. So last time we talked about the fact that the renormalization of the operators was equivalent to, you could think about it two different ways, as renormalization of operators, renormalization of coefficients. Likewise, you can think of anomalous dimensions as either running the coefficients or running the operators. So those are equivalent things. And the thing that makes them equivalent is just imposing that the derivative with respect to mu of the Hamiltonian is 0. So if I use my equation up here for the anomalous dimension of the operator, and I get, with my sign convention, a minus sign here. If I had a minus sign here, I had no minus sign here. These things are conventions. I pick some convention, and I'll stick with it. So from this equation, then we can solve for we basically have an equation that has to be true for the coefficients if we think of just stripping off the operator. So we could write it this way, just reading it off right from here, just putting this guy on the other side and then reading it off, dropping the operator. Or we could write it this way if we wanted to write it in a way that's more similar to this equation up here, where we have the anomalous dimension matrix times the coefficient. It's either from the right or from the left, and it's just a matter of transposing. So the anomalous dimension for the coefficient is determined from the one, this one here. If you know it, then you immediately know the one for the coefficient. Which shouldn't be surprising, given that we could think of the z factors as being related. The renormalization factors, the anomalous dimensions, therefore, should also be related. OK, so we'll solve this equation. It's a little bit simpler to think about, although we could equivalently solve the operator equation. So how do we solve the equation? Well, we go over to our plus-minus basis. So take the coefficient to be either C plus or C minus. Then the equation that we need to solve can be written as follows. as a simple equation, and I can even take the c, which is on the right-hand side, move it over to the left if I write log c here, because the derivative of the log is giving me a 1 over c. If I put it back over here, I would just multiply. Okay, so that's the analog. This equation here is the analog of this equation here for the operators, but now for the coefficients. Obviously, if these are numbers, there's no transpose to do. So you have to solve this equation simultaneously with another differential equation. This is a coupled equation because alpha also has a differential equation. So at lowest order, this is the beta function equation. And so if we want to take into account this equation and integrate this equation, the simple trick for doing that is to make a change of variable. So we use this equation here to make a change of variable. This is a very useful trick because it actually works to whatever order in the expansion that you might want to work. So let me explain what the trick is, and then I'll explain why that is. So we're going to change variables in this equation from mu to alpha. You see, we could think about solving this equation here by integrating. Just move this thing to the other side and integrate. But we'd be integrating in mu a function that's a function of alpha of mu. So if we can switch from mu to alpha, then we'll be just integrating a function of alpha, and that's what we're going to do using this equation. So if I write it in general, that's this equality here for any function of alpha. I say that d mu over mu, just rearranging this equation, is d alpha over beta of alpha. So I can switch the integration d mu over mu to d alpha or beta of alpha, and that's exactly what I want to do if I want to move this operator to the other side, this operation. If I work at lowest order in the beta function, then I just plug in this result. Okay, so we can switch variables from mu to alpha. And if I had higher order terms in this equation and higher order terms in this equation, I could use the same trick and I just have other integrals to do. And the integrals are pretty straightforward, so this is a useful way of proceeding. Okay, so what does that do? So now let's do that. Let's move this over and integrate. Well, we'll do a definite integral from mu w up to mu. So here we just have d log this. Integrate that just gives log between the limits. And if I didn't change variable, I would have that. But if I make the change of variable, then it becomes a very simple integral. And remember that this guy here is also just a number times alpha that we worked out last time. So this is just d alpha over alpha, and that's a simple logarithmic integral. Yeah.
I don't know if it matters, but mu w should be greater than mu, right? For
Mu w should be greater than mu. That's right.
Okay, so you're just writing integrals like that to avoid signs. Okay. I have another question.
Yeah.
How do you know that the anomalous dimensions, including the beta function, are only functions of alpha s rather than like mu?
Ah, yeah. So I'm sneaking that in here. So it follows from the renormalization structure of this effective field theory that there's only single logarithmic divergences. So like in the standard model, if you're at one loop, you only have 1/epsilon poles for the renormalization, and you're renormalizing the coupling. The same is true of this effective theory. At one loop, you only have 1/epsilon divergences, and that implies that your anomalous dimensions won't depend on anything more complicated. We will discuss more complicated cases in the future, as you know. But the structure of this effective theory and its UV structure, which I didn't go into in a lot of detail about, implies that fact.
So if
Yeah.
single logs.
Yeah. OK, so do the integral. There's some prefactor, which I'll call a plus minus, and then I get a log as I mentioned. And just for the record, this a plus minus, if I put all the factors together and put in what this number is, these would be some factors like this. And I've put in that NC is 3. So this alpha at mu w and this C plus of mu w, you should think of mu w as the boundary condition scale. So this is a differential equation. We needed a boundary condition to solve it. And the boundary condition is the value of the coefficients at the scale mu w, which is supposed to be of order mw. Typically what that means is you could take a common choice, which would be just to take it equal, or you could pick twice or half, and these are the most common choices that people pick. So the way that you should think of that, this guy in the denominator, is you should think that he's really a fixed order series in alpha of mu w. Something that you would calculate order by order in perturbation theory. And you'd be determining the boundary condition. We'll talk about how you would do that a little later today. But for now, just think of it as a series in alpha of mu w. And it doesn't have any large logarithms. And as Ilya said, you want to think of this mu as some small scale, some scale that's less than mu w, and you want it because you're thinking of evolving the operators to a scale less than the scale where you integrated out the particles. I'll draw that picture in a second. So we could take the exponential of that equation, and then we can write C of mu is equal to something that we've determined. Take the exponential, move this guy to the other side. Remember that a plus minus are just numbers. We can write the solution in this way, where we determine this guy by thinking about doing a matching calculation at the high scale. We determine it to be a half already at the lowest order, so think about sticking in a half here. And then this factor here is what you get from the renormalization group. And you can see from this form right here that you've summed up an infinite number of logarithms. It's exponential of a number times log, and if I were to expand that out, in alpha at some fixed scale, it would be an infinite series in logarithms. OK, so what do we want to pick this mu to be? Well, we're thinking about the process B goes to C u bar d. if you think about this process in nature, the scale it's in the initial state here is the B meson mass. So you'd like to take this scale here, not at MW, but down at the B quark mass. So we want mu to be of order MB. And then you have a large hierarchy because this is much less than MW. 5 GeV-ish, 80 GeV, 80 GeV. So our result here sums what are called the leading logarithms. Which is denoted by LL. And schematically, the lowest order term was a half. And if we were to expand higher order terms and think about what logarithms we're talking about logarithms of MW over MB. And the series, if we were to expand it, would look like this schematically, without worrying about the coefficients. An infinite series where each term has one alpha and one log. So the counting that you're doing in this type of setup, where we would think of using this equation to go down to the scale MB, is that you're counting this parameter as order 1. And you're saying anytime I see a log of MW over MB times an alpha, I'm not going to count that as order alpha, I'm going to count that as order 1. And that's why I have to sum up this infinite series. So the physical picture of what we've said here is the following. So the basic physical picture would be that there's two scales, MW and MB, which are physical scales. You want to get rid of the scale MW. You do that by going over to this electroweak Hamiltonian. But then you have to renormalization group evolve that Hamiltonian down to the scale where you want to do physics, which is this scale MB. And when you do that, there's some choice in the matter, and we've been careful to parameterize that choice. We said that you pick a scale that's of order MW, which we called mu W. And then we said you pick another scale that's of order MB, which we called mu. And you actually do the renormalization group between these two. You could pick it to be exact mu W exactly MW and mu equal exactly MB. That would be kind of the simpler story. But it is actually important that once you go beyond the lowest order to keep track of the fact that you have this freedom. And that's why I've kept track of it here. So what that means is that in terms of counting, you've counted this, but logs of mu W over MW are counted as order 1. And then down here, logs of mu over MB are counted as order 1 numbers. Could be 0, but 0 is order 1. Not enhanced such that they would compensate for a factor of alpha. And this is the renormalization group evolution, or the running, that sums up these logarithms here, which are the large logs. And that's pretty simple. It just gave this factor. Okay, and that's pretty common in QCD to get factors like that, alpha at one scale over alpha at another scale raised to a power. That's a very common thing to get from renormalization group evolution. Okay, any questions so far? How many people have done the calculation of the anomalous dimension for 4 fermion operators in some other course? It's a common problem. Nobody. All right. That means you'll see it on homework.